Hi, welcome to Introduction to Econometrics course, and today's topic is devoted to two-variable regression analysis, or basically regressions with one independent or explanatory variables. So in order to understand the idea, behind regression in general, we first have to discuss the notion of conditional mean. So based on this purely fictional and hypothetical example I just came up with. So as you know, basic macroeconomic neoclassical theory predicts that higher values of capital per worker stock are associated with higher values of income per capita. So, following this causal relationship described by theory, we assign capital per worker stock indicator the role of the independent variable, or X, and we assign income per capita indicator the role of dependent variable, or Y. So basically it means that income per capita depends on the value of capital per worker stock. So just for the sake of simplicity, assume that there are only 6 possible values of capital per worker stock possible in the entire population. So it's 100, 200, 300, and so on and so forth, up to 600. And here you have different values of income per capita, depending on the value of capital per stock. So basically in this column, you have income per capita for all the countries in population where the value of capital per worker stock is equal to 100. Here you have the values of income per capita for all the countries where the value of capital per worker stock is equal to 200, and so on and so forth. So if we calculate unconditional mean, for this entire population, just, summing up the values of income per capita in these countries and dividing it by the number of countries in population, you will get something around 2,200. But this is not what we are interested in. So basically conditional mean stands for the expected value of Y depending on the value of X. So here you calculate the average value of income per capita for all the countries where the value of capital per worker stock is equal to 100, and you've got 440. Here you calculate the average of income per capita for all the countries where the value of capital per worker stock is equal to 200. Then you get 593. If you calculate the average of income per capita for all the countries where the value of capital per worker stock is equal to 300, you should get something around 700, and so on and so forth. So basically conditional mean tells me what is the expected value of per capita income depending on the capital per worker stock. So for instance, if I know that in the country the value of capital per worker stock is equal to 100, then I expect to see income around 440. If I know that in the country the value of capital per worker stock is equal to 600, then I expect to see per capita income around 3,172. With some deviations, of course, but we will discuss this later on. So very basically, if you put on the graph capital per worker stock indicators on horizontal axis and the value of per capita income on vertical axis, just depicting those conditional means. Again, 440 next to 100, 593 next to 200, and so on and so forth. Then you should get something like this. And basically, the combination of all the conditional means corresponding to the different levels of capital per worker stock stand for regression line. And this makes sense, because since the value of capital per worker stock increases, you also expect the expected value of income per capita increase as well. This follows the nature of data, and this can be very easily explained by macroeconomic theory. So yeah, basically the regression line is just the combination of all the conditional means corresponding to all the possible values of the independent variable. So linear regression looks as follows. Here you have the expected value of y depending, constrained to the value of x, or basically conditional mean. Beta 0 stands for, independent parameter, or basically in this case it will be just the value of the vertical intercept of the regression line and conditional mean axis. X stands for the independent variable, that's why you put this on the horizontal axis, and beta 1 is basically the slope of the regression line. So this is the rate of change of the conditional mean reflecting the change in the independent variable. So under the linear regression, we assume that this rate of change is constant. So the slope of the regression line would not depend on the value of x. We will get back to this. So when we say linear regression, basically we mean linearity in terms of the independent variable. Or, in other words, we assume that the independent variable is represented by the linear term, or that there is a linear relationship between the dependent and independent variable. Linearity in terms of parameters means that parameter, like beta 1 or coefficient, is represented by the linear term. So here, for instance, you can see the example of linear regression, which is linear in both variables and parameters, since beta 1 and x are represented by the linear terms. Here, you've got nonlinear regression in variables, because x is represented by the square term. Still, this regression is linear in terms of parameters. Finally, here you've got nonlinear regression neither in variables, neither in parameters, because both x and beta 1 are represented by the square terms. Okay, so a brief note on linearity. Linearity in variables implies that the rate of change of the dependent variable is constant. So basically it means that it does not depend on the value of independent variable. However, this is not always true, and nonlinearity can be justified by nature of data, economic theory, or actually both of them. Okay, so here you've got the neoclassical production function, a typical neoclassical production function, where y stands for the level of output or income, aggregate income in the economy. A stands for technological coefficient, depicting the level of technological advance, stock of human capital, and so on. K stands for the stock of physical capital. L stands for the stock of labor, or the size of the labor force. Small a stands for parameter, denoting the degree of capital intensity of the particular production technology. It always takes the value between 0 and 1. And here we've got constant returns to scale. So it means that we can easily define per capita production function by dividing both sides by the stock of the labor force. So here you've got this. And finally, you've got the per capita production function, where y stands for the output or income per capita, and small k stands for the stock of physical capital per capita, or capital per worker ratio. So as you can see, this function is definitely nonlinear. So actually this is an increasing function since coefficient a is positive, and this is a concave function since it's smaller than 0. So in line with the law of diminishing marginal product, in line with the law of diminishing marginal product, you expect this function to be increasing but at decreasing rate. So basically each addition to capital will result in smaller and smaller increase in output per capita. So basically, yeah, you expect this function to grow relatively fast when the stock of capital is rather small, and you expect this growth to diminish once the stock of capital increases. Okay, so here is the linear regression. I will show you how to do this. So this is based on the set of data which was collected for 206 world economies for 11 years from the World Bank data set. Like, this is convergence, you know, a general data set. Okay, this is how you import data to Gretel. And since I have panel data, I would definitely like to assign panel specification. So I click panel. I have index variables, which mean that I have values assigned to country and time. Here you've got the name of this series. And yeah, 206 countries observed for 11 years, which is fine. Okay, so then you click this icon. I assume that capital is independent variable. That's why I put it on x-axis. And I assume GDP per capita to be the dependent variable. Ta-da! So here you've got this graph, the same as you have on the slide. Here you have this. So yeah, it's still possible to design a linear regression line, you know, because this is the problem. There is nothing which would prevent you from doing this. Even though, like you can see, based on those red crosses, which stand for the empirical observations, that actually, you know, linearity is not the best approximation for the capital per worker and GDP per capita value. So, you know, from my perspective, it looks more like an increasing concave function. So, you know, like linear specification might not be the best way to depict this relationship. But nevertheless, yes, as I mentioned before, it's still possible, even though it undermines the validity of your regression analysis. However, like nonlinear specification will be discussed later on, not during this lecture. Okay, so here you have the value of intercept. So the value of GDP per capita when the capital per worker stock is equal to 0. And here you have the coefficient, 2.36. So this means that each, like 1 unit increase in capital per worker stock, in my case it was expressed in the current US dollars, will result in 2.36 units increase in the value of GDP per capita. So this is how you interpret this. So again, when you have a simple linear specification, you always base your analysis on the original units in which those variables are expressed. So for instance, if I express capital per worker, which is ridiculous and stupid example, but just imagine for a second, if I express capital per worker in, let's say, tons of machinery, then I would interpret this as follows. Increasing capital per worker stock by 1 ton of machinery results in $2.36 increase in GDP per capita, because GDP per capita was expressed in constant US dollars. Okay, so as you can see on this graph, you know, even though regression line comes through some of the empirical observations described by the red crosses, there is no perfect coincidence between them. Like, for instance, in this case, like, let's say for this particular capital per worker variable value, which is 15,000, I would expect income per capita to be around 40,000. However, you know, when I look at the empirical observation, I see that actually it's about 80,000. So the distance between empirical value of the dependent variable and predicted value of the dependent variable is described by the stochastic error term. So here you've got this. So stochastic error term is basically the difference between the empirical observation and what you predict based on the analysis of conditional mean. So this is just the difference between those. In the same manner, you can express the empirically observed value of the dependent variable as yi and see it as the combination of predicted conditional mean and stochastic error term. And since the predicted conditional mean is equal to beta 0 plus b1 times x, you replace this with that, and this is what you've got as the result. You also expect the conditional mean of the stochastic term, conditional to the value of the independent variable, to be equal to 0. Later on, we're gonna discuss, the importance of this and what happens to regression when this assumption is violated. So, why do you need stochastic error term? First of all, as we discussed before, you need this because sometimes your model is poorly specified. So, in line with the economic theory and common sense in general, I would rather specify this regression line as the increasing concave function. However, since I analyzed it using linear trend, there is some inevitable distance between my empirical observation and linear trend. So that's why poor model specification or incorrect functional form is one of the reasons behind the existence and importance of stochastic error term. In addition, sometimes, there might be the case that there are other potentially important variables except of the variable you actually analyze. So in this case, capital per worker plays the crucial role. It's assumed to be the core of my analysis based on economic theory. However, as you can probably guess, there is plenty of other factors which might potentially affect output per capita, including more important factors like quality of education, quality of infrastructure, quality of institutions, whatsoever, and also including less important factors, like probably natural resources abundance, location next to international trade routes, and so on and so forth. So this is the idea. Sometimes those peripheral variables are actually important, so they contribute and they affect the value of the dependent variable, but they are too hard to account for, and their combined effect might be just stochastic. Like they interact. Some variables are important only under the presence of other factors and effects and so on. So it's better to describe them as some stochastic deviation or as the stochastic error term. So additionally, your theory might be incorrect. So sometimes conclusions made based on purely theoretical analysis do not incorporate, all the entire variety of factors which are present in reality. So theory might be misspecified, it also happens. And that's why the model, even if it's designed based on, in accordance with the theory predictions, might be incorrect. So yeah, then you will still have the distance between the empirical observation and predicted mean, predicted by the regression analysis, and it will be incorporated in the stochastic error term. There might be the result of poor proxy variables because, as we discussed during the first lecture, some variables which are discussed quite commonly under economic theory, for instance, let's say human capital, have no perfect proxy representation. So you can take mean years of schooling, secondary / tertiary education enrollment rate, and so on and so forth, but it will never be the perfect proxy for the human capital. And then it might also result in the difference between the empirical observation, and what you predict based on theory. Okay, so the next thing we have to discuss is, the difference between population and sample. So basically, population consists of all the agents of interest. For instance, if I analyze the relationship between capital per capita and income, it makes sense for me to collect all the data, for the entire historical period for all the available countries. So then I will have population. And sample is basically some portion of population. So let's say it can consist only of developed or only of developed economies. So usually we assume that a good sample shall be a representative sample. However, this is another topic discussed in another video. But this is not always the case. Sometimes you can design subsamples just, to analyze the difference in effect of the independent variable on the dependent variable. So maybe it's easier to show you based on some example. So again, here you can see the regression line, which was designed based on 206 economists observed for 11 years. So here, $1 increase in capital per worker stock results in $2.36 increase in the value of GDP per capita. However, you can also do it based on subsample, only for developing countries. And this data set is also available on data repository, on the SOBA. So in this case, when you analyze developing countries, you will see that actually this cumulative effect, not cumulative effect, but let's say the effect of capital per worker on GDP per capita is stronger. So now we have 2.54 coefficient, which means that $1 increase in capital per worker stock value results in $2.54 increase in GDP per capita value. Here you have the subsample of the developed countries. And here the value of coefficient is 3.13. Also, you have the different value of the intercept. So you see that once you manipulate, the size of the sample and the nature of the sample, like intrinsic values of agents constituting this sample, you will get a different result. So again, if my task would be to define some uniform effect, and let's say collecting such a huge amount of data would be impossible, I would like to pick some developed and developing countries in order to ensure representativeness. However, if my task is to demonstrate the difference in effect capital per worker increase causes on GDP per capita in developing and developed countries, then I can just design subsamples consisting of developing and developed countries. Okay. So I believe it was fine. So your practical task for this week is to go to the World Bank database. You have to choose one country, with the adequate available number of observations, and create the time series data set for two indicators, which are poverty and literacy rate. So you have to specify poverty as the dependent variable and literacy as the independent variable. You also have to explain the logic behind this specification, You have to find some justification in economic theory. Using Gretel or Ifuse, you have to run the linear regression, just as I demonstrated you today using Gretel. You have to interpret the coefficients based on the units in which the indicators are expressed. You have to look at the set of empirical observations on the graph, like here they are represented by those red crosses, and based on this you have to tell whether empirical trend indeed seems to be linear. Then you have to comment on the possible reasons behind the difference between the empirical and predicted values of the poverty indicators. Actually, here you have to have between. Sorry for this. Okay, so comment on the possible reasons behind the difference between the empirical and predicted values of the poverty indicator. So once you are done, you have to send it to me, and probably you know, if you still have some questions or doubts, or you just struggle with this task, we can discuss it next week. So please keep in mind that for your project, you will actually have to design, your own econometric regression. That's why treat it as the first step, as some initial practice. If you fail to do this task, probably you will also fail to do the project, and you will fail to pass this subject. Okay, so on this pessimistic note, that's it for this week. Please do the task. Please send it to me by Saturday. And yeah, that's it. Thank you for your attention.